Hello, good afternoon, everyone. I need someone to confirm if you're hearing me clearly. Is everyone hearing me clearly? Okay, thank you so much. Thank you for confirming that. Of course, today it's going to be our final preview before the uh, you know, uh, final exam. And of course, I also want to say I've been recording. I recorded the revision that we had on Monday, and of course, I'm also having this in recording as well. So, the purpose of the meeting today is just to make it short, and of course, gonna tell you, some information that you need, for the final. Of course, the final exam will be written in person, okay, in the same class of your lecture, of course, on Monday, I think 18. So you can check the syllabus. It doesn't change. It remains, the final exam was set, the venue and the date and time of the final exam was actually scheduled at the beginning of the semester by the university. So but I'm going to give you a clue today about, of course, before now, I've already told you some areas, that will be covered in um, in the final. And of course, you're going to spend 2 hours in the final. You got a lot of time. 2 hours will be spent in the final. And you know what? There's going to be 5 questions with multiple parts in this exam. And what I need you to do is to listen good, so that you could actually be able to know, you know, I'm actually going to tell you the area of each question. Okay. I need you to give me a thumbs up or to talk if you are ready. Are you all ready? Okay. Thank you so much for that. I can see you are. I also need somebody to talk. I really want to know if I can hear you. I need someone to talk to say, okay, I'm hearing you.
I can hear you.
Okay, thank you so much. Okay, so there's going to be 5 questions, like I said. Okay, in the exam, there's no multiple choice. It's just going to be 5 questions. Okay, and let me tell you, the exam will be theoretical. Okay, now I need you to listen now as I'm going to unravel the 5 areas that will be covered in this exam. Now, in problem number 1, I'm actually going to test your knowledge of method of movement and the maximum likelihood method. You're going to be given a probability distribution. What I need you to do is start revisiting the probability distribution where every probability distribution is parameterized. Every probability distribution has parameter. Whether you want to talk about exponential, you want to talk about gamma, you want to talk about normal, you want to talk about negative binomial, and so on like that. I just need you to revisit the distributions that we've done. Okay, they're going to give you a particular probability distribution that has a parameter, and I'm actually going to ask you to, you know, use the method of movement. Okay, the method of movement. Okay, to obtain the estimator for the parameter. Okay, now don't forget, if you want to do method of movement, okay, remember that the method of movement, I'm going to do something right now. I'm going to share my whiteboard. Okay, I'm going to share my whiteboard. Remember, when I'm talking about method of movement, so what method of movement implies is I'm actually going to equate the mean, the expected value of X of a particular probability distribution to the sample mean. Okay. And when I equate that, then I'm going to, for example, let me give you an example of a particular distribution. Or let's say you have like Poisson distribution, for instance. Okay. If you have a Poisson distribution, for instance, where you have exponential raised to power lambda and lambda raised to power x over x factorial. And of course, you need to be able to know what does it mean? What is the expected value of x for this distribution? That is lambda, right? And at times, the distribution may be continuous, where you are going to be the one that will figure out the expectation of x. You know, so right now, if I'm actually going to equate this guy to x bar and believing that the moment estimator now, MOM, is actually x bar for the Poisson distribution. Okay, so the idea behind the method of movement is when you derive in a situation where you are not given the expectation of a particular distribution, all what you just need to do is to be able to know how to obtain the expectation of x. Now, when you are given a continuous probability distribution, don't forget you're going to do integral x f of x dx and use the state space of the distribution to figure out what the expected value of x is going to be. So when you get the expected value of x, then you're going to equate that to mean. So now in the same question, okay, in number one, I'm also going to ask you to find the method, the method of movement. The maximum likelihood estimator. Okay, the maximum likelihood estimator. If you have a particular distribution, okay, you have a particular distribution, okay, maybe the distribution, I'm just assuming now, let's say the distribution is binomial, where you have n combination x, okay, p raised to power x, and 1 minus p raised to power n minus x, okay, and they wanted to get the maximum likelihood. Of course, you're going to get the likelihood, and after getting the likelihood, okay, don't forget, when you get the likelihood of a distribution, okay, you can actually take the log of the likelihood. After taking the log of the likelihood, then you differentiate with respect to the parameter. Okay, when you differentiate with respect to the parameter, you're going to set that to 0 and you solve. Like here now, if I want to go, if I do the, this is actually going to be n combination xi p raised to power that, 1 minus that. Okay, now when you take a look at this guy now, it's actually going to be, okay, I'm actually going to have this guy, then p raised to power summation x, 1 minus p raised to power n minus summation s. So the next thing I just need to do is to take the log. When I take the log or logarithm of that, I'm going to differentiate with respect to the parameter p. I'm going to set to 0, then I'm going to solve for p. That will give you the maximum likelihood estimate. Now, what question one is going to, question one part one is going to talk about is they're going to give you a distribution. They're going to ask you to obtain the method of using the method of movement to get the estimator on the same distribution using the maximum likelihood to get our estimator. And I'm going to ask you to compare the two. I'm going to ask you to comment whether you have the same expression for the estimator or not. That is just going to be question one, part one. It could be any distribution. Okay, it could be any distribution. Okay, but particularly I will advise that you revisit continuous. Is more likely to be continuous probability distribution. Okay, is more likely to be continuous probability distribution. So that's what that is what I'm actually going to have. That is what I prepare for. That is question one. That is going to be question one. Okay. Now, is there anyone who need clarification before I go to what the problem two is likely going to be? Any question, any clarification? Can you confirm again if you are still hearing me clearly? Is everyone still hearing me clearly? Okay, thank you so much. Thank you so much for that. Now, what question two is going to be? Question two is going to talk about consistency. Okay, it's going to ask you to investigate for consistency and investigate for unbiasedness. That is question two, part one. Okay, now you are given an estimator. They're going to give you a distribution. Okay, give me 1 second. Okay, you were given a distribution. Okay, let me just assume. I'm just assuming now. Let's say you have an exponential distribution. I'm just assuming. Okay, now on this distribution, maybe they give you, oh, expected value of S is theta. The variance of S is theta squared. And they now have an estimator. The estimator may actually be n plus 1 x bar, and they ask you to investigate the unbiasedness of the estimator. Not only that, they also want you to investigate the consistency. Let me tell you this. If you want to investigate consistency, you need to be able to know whether you are working with an unbiased estimator or not. If you are working, the reason why why investigating for unbiasedness become necessary when you want to investigate consistency is because for you to be able to know whether you're going to make use of the variance of the estimator or you're going to make use of the mean square error. Now, when the estimator is unbiased, then it means for consistency, you're actually going to investigate the variance. Okay, so like I said, if you want, the first thing is, what is the expectation of this guy? Which is going to be the expectation of all of that, which is going to be, I'm just assuming, n plus 1, expected value of x bar. And you know what? Expected value of x bar is the same as expected value of x. And you've been given the expected value of x right here. So with that, you'll be able to know, if your expression at the end of the day, if the expression actually gives theta, that would mean the estimator is unbiased. If the estimator is unbiased, the next thing they're going to ask you to investigate the consistency. So if it is unbiased, it means if you want to investigate consistency, is actually going to be taking the limit of the variance. So taking the limit of the variance, it means you need to derive the variance of the estimator. So, the other time I said, the estimator, the other time I said the estimator is theta cap, okay, n plus 1 x bar. Okay, now I need the variance. Okay, I need the variance of the estimator. How do I know I need the variance of the estimator? I'm going to use the variance of the estimator if the estimator is unbiased. But if it is biased, then I need to get the mean square error, which is going to be the variance plus the square of bias. And don't forget, if you want to do that, it's more or less like you're actually going to have whatever you are given and that. And of course, that guy is going to come out, that you're going to have the variance of x bar. Now, don't forget, you've been given the variance of x here. And don't also forget the variance of x bar is going to be the variance of x divided by n. Don't forget, divided by n. In investigating for consistency, you got to do x tends to infinity. When x tends to infinity, we expect the variance of an unbiased estimator to converge to zero. Okay, that's to converge to zero. Now that's how, so like I said in problem 2, part 1, okay, I'm actually going to give you a distribution, and I'm going to give you the mean expectation of the variance, expectation of the random variable and the variance of the random variable. And I'm also going to give you an estimator, and I'm going to ask you to investigate the unbiasedness of the estimator. And not only that, I'm also going to ask you to investigate for consistency. Is there anyone who need clarification on that? That is going to settle problem 2, part 1. Any question?
I have a question. So
Go ahead.
sorry, I just missed this. Did you say that that estimator was unbiased or biased?
I don't know. You know, what I can tell you is, if I ask you to investigate for unbiasedness,
Yeah.
okay, there's possibility, maybe in the question.
No. Just like the example you just did.
Oh, the example I just did
Yeah.
is going to be biased
Yeah. So then
because
would you take the variance or would you take
no,
the mean
no,
squared error?
I'm going to take the mean square error.
Okay, thank you. I
You're
was
welcome.
like, wait, okay.
Okay,
Thanks.
you're welcome. So let me just say this in general, right? In general, if even if they did not ask you to investigate for unbiasedness, if they ask you question on consistency, you need to investigate unbiasedness first. So the reason why you need to investigate unbiasedness first is for you to be able to know whether you're going to take the limits as n tend to infinity for the variance or for the mean square error. So like the example that I did where I said n plus 1 into x bar, of course, that is going to be bias. And if that is bias, then I would determine the bias. When I determine the bias, what I'm just going to do, and let me also say, let me write this. If you want to know bias, if you want to start, like if you can do this, bias equal expectation of the estimator minus theta. When this give you 0, when bias equal to 0, then it means the estimator is unbiased. But when the bias is not equal to 0, but equal to an expression, that expression is the bias. And don't forget, if you want to do the mean square error of the estimator, is actually going to be the variance of the estimator plus the square of the bias. Don't forget that. And if I want to investigate for consistency, then it means I'm actually going to do x tends to infinity, the mean square error of the estimator. Okay, when the mean square error of the estimator converges to 0, then I'm actually going to say that bias estimator is consistent. But if the bias equal to 0, then I'm actually going to make use of the variance. Okay, now when I make use of the variance, when the limit x tends to infinity of the variance converges to 0, then I'm actually going to say that unbiased estimator is consistent. Okay, so that's of problem 2, part 1. Okay, now I want to go into problem 2, part 2, because there's a lot of questions in part. Problem 2, part 2, okay, I'm going to give you a continuous probability distribution, and I'm going to give you the mean and variance of that distribution. I'm going to say that again. Problem 2, part 2. I will give you the mean and variance of a continuous probability distribution, I'm also going to give you the expression for the probability density function, but I'm also going to give you the expectation of X and the expectation of the variance of X. And I'm also going to ask you to find the method of movement again. Finding the method of movement, then find the method of maximal likelihood. Okay. Then I'm also going to ask a question now, based on the method of maximal likelihood, based on the estimator that you get in the method of maximal likelihood, I'm going to ask you to investigate whether it is biased or not. Let me tell you this. Whether you have a moment estimator, whether you have a maximal likelihood estimator, or whether you have whatever estimator at all, it is the same way that we investigate unbiasedness. All what I just need to do is to take the expectation, okay, the expectation of the estimator minus theta. That is a bias. When the expectation of the estimator, whether moment estimator, whether maximal likelihood estimator, whatever estimator at all, is the same way to investigate the unbiasedness. So the bias is going to be expectation of the estimator, okay, minus theta. Okay, so based on the maximal likelihood estimator, which means if you want to get the maximal likelihood estimator, let me tell you the reason why I gave you the mean and the variance is for you to be able to get the method, for you to be able to get the estimator using the method of moment. Okay? But if you want to get the maximal likelihood estimator, you're actually going to make use of the distribution. All what you just need to do is to get the the likelihood of the distribution, then take the logarithm of the likelihood, then differentiate the log likelihood with respect to the parameter, set it to 0, then solve for the parameter. That becomes the maximum likelihood estimator. Okay, and when you get a maximum likelihood estimate or whatever estimator at all, you want to investigate for unbiasedness, is the same way that we investigate. The same we're going to investigate that. Now, they say another question there is going to say, is the MLE consistent? Oh, if you want to know whether the MLE is consistent, I'm going to say this again. You want to know whether the MLE is consistent, then it means you actually take a look at this. Let's say, for instance, after I've gotten, I'm going to give you an example now. Okay, I'm actually going to give you an example from exponential distribution. For instance, if I have f of s equal 1 over theta exponential raised to power days, okay, and I want to get the maximal likelihood, okay, and after getting the maximal likelihood, I want to investigate for unbiasedness property, and I also want to investigate for consistency. What am I going to do? Okay, if I want to do that, okay, and you know, here you've been given expected value of s to be theta, and you'll be given the variance of s to be theta squared. Okay, of course, here, you know, the method of movement is going to be easy, right? The method of movement is just going to say, oh, expected value of s equal to theta, okay, which is going to be equal to x bar. So which means here the theta cap MOM is going to be x bar. Okay, this is the method of movement estimator. Now, let's say they wanted to investigate for the whether it is unbiased or not. Whether it is unbiased or not, you're going to do expected value of this theta cap MOM is going to be equal to expected value of x bar. An expected value of x bar is the same thing as expected value of x, and that is given here, which is equal to theta. You see that now? So based on the exponential now, okay, the moment estimator for exponential is unbiased. The estimator now is unbiased. You see that? That is how. Now, now that I know it's unbiased, don't forget, you can see the reason why I need this guy here, right? It's unbiased. Now, if it is unbiased, I can also investigate a moment estimator for consistency. Okay. Now, how am I going to investigate that for consistency? I need, because it's some bias now, I need the variance of the estimator, of the moment estimator. Now, if I want to get the variance of the moment estimator, oh, it's going to be the same way. Oh my God, it's going to be the same way. So it's going to be variance of theta cap MOM, which is equal to the variance of X bar. And what is the variance of the X bar? It's the same thing as the variance of X over n. Oh my God. This is the variance of S given to be theta squared. And, this is going to be automatically theta squared over n. Now, this is the expression for the variance. Now, when that is the expression for the variance, you know what I'm going to do? I'm just going to find the limit as n tends to infinity. Okay, so it's going to be limit, okay, n tends to infinity, okay, of theta squared over n. Of course, that guy is going to converge to 0. What have I done here? I've investigated for the whether the moment estimator that I got from the exponential distribution is consistent or not. And I've also shown you how to investigate the unbiasedness. How do we do this for maximum likelihood? I'm going to show you now. Estimator. Is everyone still hearing me? Okay, thank you so much. Thank you for confirming that. Now I want to come into the maximum likelihood now. For the maximum likelihood, I need to first get the estimator, right? And after getting the estimator, the next thing I'm actually going to do, okay, is to, to investigate, the unbiasedness property and the consistency property. Now, we take a look at this now. Let's get the likelihood of this guy. The likelihood of that, of the likelihood of the f of s will be equal to this guy here, 1 over theta, this guy here, and of course this guy is going to be 1 over theta raised to power n exponential. I'm actually going to have this guy. This is the likelihood of the exponential distribution. Now, the next thing that I'm actually going to do, okay, go
Question.
ahead. Go ahead.
So when you solve for the expected value of X bar, why wasn't it theta over n?
No, the theta square over n that I got was the variance of X bar. If you take a look at this, the expected value of X is theta.
So then
So,
why isn't the expected value of the sample mean theta over n?
no, expected value of sample mean will be the same thing as expected value of X. You remember in class? Expectation of
Um,
S is the same thing as expectation of Y bar, of S bar. They don't change. The only thing that changes the variance. You remember we derived that theorem in class in chapter when we started early, like when we started chapter 7. So
yeah.
please take note always.
But when we did a problem on an earlier exam and we actually knew the sample size of an exponential distribution, it was equal to 3. So when we took the expected value of the sample, it was theta over 3.
This is what happened. It depends on the specification of the density. There are some the exponential distribution can be presented in different ways.
Mm-hmm.
Based on this guy, okay, I want to believe based on what you see here,
Mm-hmm.
the expected value of S is theta.
Mm-hmm.
There
That
are
makes
some that have a different expression that may be a theta over whatever, like you said.
mm-hmm.
You understand what I mean? But the theorem that I'm proving to you is expected value of X bar. It is always expected value of X.
Okay.
It doesn't matter, irrespective of the sample size, expectation of the mean is the expectation of X.
Okay.
But the one that is not the same, please take note. This guy, the variance of X bar is not the same as the variance of X. So the variance of x bar will be variance of x divided by n. Does that make sense?
Yeah.
All the time.
Okay.
All the time.
Okay,
Okay,
thank you.
you're welcome. Now, moving on with the maximum likelihood. Okay, moving on with the maximum likelihood, I can simplify this. It's still going to be that. You need to do some mathematical work. Now, right now, what I need is to take the log. Okay, don't forget, you're going to take the log. We normally take the log of the likelihood function. Okay, so taking the log of the likelihood function. So the log of this guy now, okay, maybe I should call that N, is equal negative n log theta minus summation x over theta. When I said I'm taking the log, it has to be a natural log. Now, right now, this is what I got. What I'm going to do now, and then I need to differentiate with respect to theta. Don't forget the method that I'm actually using is a method of maximum likelihood. So what I'm going to do now, I'm going to do the L, the theta, okay, which is going to be negative n over theta. And, if you take a look at this, I think that's going to give you summation x over theta squared. Then you're going to set that to 0. Now, when you set that to 0 now, you're actually going to have summation x that equal n over theta. Okay, this guy cancel that. And what is going to be your theta cap now? So you're going to say theta cap MLE. So your theta cap MLE now, okay, is actually going to be summation x over n. And what is summation x over n? Theta cap MLE now is equal to x bar. If you notice for exponential, okay, the moment estimator for exponential is the same as the maximum likelihood estimator. The moment estimator the other time gave us x bar. The maximum likelihood estimator also gave us x bar. Okay, now which means the same way I investigated for consistency and for unbiasedness is the same way I'm going to do this. So for this one now, if I want to investigate for the unbiasedness, what I'm just going to do, I want to investigate the unbiasedness of maximum likelihood estimator. Okay, so if I want to do that right now, okay, so I'm actually going to do expectation of the MLE, okay, which is going to be equal to expected value of x bar because that gave us x bar. And what is the expected value of x bar? Is certain expected value of x. And what is the expected value of s from the distribution? That is going to be theta. Okay, which means it's unbiased. And when it is unbiased, then it is time now. If I want to investigate consistency, I'm actually going to focus on the variance. Okay, so focusing on the variance now, so which means the variance of theta cap MLE is now going to be the variance of x bar. You remember the other time, the variance of x bar is going to be what? The variance of x bar, don't forget the definition. Anytime you get to x bar, it's going to be the variance of x divided by n. And what is the variance of s according to the distribution? It's actually theta squared. Okay, divided by n, I'm done. Okay, so that is how problem 1 and problem 2, oh my God, because of the time, I got to move right now. Now, I'm actually going to stay 10 minutes late. Okay, if you have class, you can actually leave at 3:20. Okay, but I'm going to stay 10 minutes late on whatever I'm going to be saying is recorded. And of course, I'm going to publish that. Okay, now I want to go into problem 3. I think I've just reviewed to you problem 1, problem 2, the expectation. Then I'm going to go into problem 3. Now in problem 3 will test your knowledge of, best critical region. We're going to give you a distribution, okay? And we're going to have a simple hypothesis where maybe they could say, you have a distribution. Let's say, for instance, I'm just assuming using exponential again, or maybe you have exponential distribution, okay, and maybe this is given and theta is unknown, and maybe they believe maybe theta that is unknown, maybe 1, and alternative, maybe it's saying theta equal 1.5. Of course, you know, this is a simple hypothesis. And question 3 is going to say, okay, derive the test, okay, you know, with the best critical region. The test with the best critical region, we actually need, you're going to use the knowledge of Neyman-Pearson-Neyman theorem. Okay, so, and after that, they said, find the most power, that is, you are asked to find the most powerful test, okay, with a 5% significance level for testing the simple non-hypothesis that theta equal to 1. And there's something I wanted to pay attention to. I needed to watch out for these two questions. One, they could talk about one observation. If they say one observation, at times they could say one observation. At times they could say they have more than one observation. I'm talking about sample size. Please watch out. Now, in a situation where they said one observation, there's going to be a question that will talk about one observation. How do I handle the one of one observation, and how do I handle the one that is more than one observation? The one of the one observation, you don't get the likelihood because the sample size equal to 1, but you're going to do the ratio, okay? You're actually going to do, okay, the ratio, okay? I want to confirm again if if everyone's still hearing me clearly. Is everyone still hearing me clearly? Okay, thank you so much. And thank you for, confirming that. So what I'm trying to talk about is, if you take a look at this guy now, I need to 4 of us get for one observation, okay? We normally use likelihood of the non-hypothesis divided by likelihood of the alternative, okay, less than K. Okay, now you're going to take a look at this guy, plug in 1, because here when the non-hypothesis is true, if you plug in 1, it's going to be this guy, right? Divided, plug in at 1.5. Okay, it's going to be 1 over 1.5, this guy over 1.5, now less than K. Okay, now when you take a look at this is what you're actually going to simplify. You can see here, you didn't see any summation X. It's just X because it is one observation. When you have one observation, we don't say summation X. When you want to sum X, that is when you have more than one observation. But a situation where you only have, just one observation, it's just going to be X, then you just simplify that. Okay. Now, like I said, they're actually going to ask you to develop the most powerful test. You follow what we've done before. And not only that, what of in a situation where they gave you a critical region? Okay, please pay attention. Maybe they gave you a critical region. At time we could give you a critical region, even though that is the region that you are constructing. Okay, now they give you a critical region that X, X is greater than 0.6. I'm just assuming. Okay, if they give you critical region, then they're actually going to ask you to find, the probability of type 1 error and probability of type 2 error. Now, I need you to pay attention now. Okay, I need you to pay attention now. For this, the other time, we are testing hypothesis, theta equal to 1, against the alternative, okay, theta equal 1.5, and the distribution was actually 1 over theta exponential this, right? And maybe they now, in another question like question B, after you've already derived the best critical region, another question is still going to say, okay, you know what? Let us assume we give you a rejection region, a critical region of X greater than 0.6. compute type 1 and type 2. Compute the probability of type 1 error and the probability of type 2 error. Let me tell you this, if you want to do that, it means you want to get alpha. And alpha is going to be equal to the probability of type 1 error. And what is the probability of type 1 error? The probability of type 1 error is actually saying, okay, when you reject the null hypothesis when it is true. Okay, the probability of rejecting, the probability, of rejecting HO, okay, given that HO is what? Is true. Okay, now what are you going to do? You reject HO given that HO is true. Now, I want to award an extra credit now. Okay, before awarding this extra credit, I need somebody to confirm again if you are still hearing me clearly. Is everyone still hearing me clearly? Thank you so much. Okay, thank you for confirming that. Now, if I want to answer this question, can somebody tell me for extra credit? If I want to get alpha, which is the probability of, and this is my critical region, this is my rejection region, this is the distribution. Okay, how am I going to find the probability of type 1 error rejecting H0 when H0 is true? Can somebody tell me?
You just find the probability that the critical value is within the rejection region,
Okay,
or the
now,
highest tail of the rejection region, you should say.
so which is going to be, tell me, what will be the range of the integral?
Ooh.
You are right, you tell me that I'm going to find that probability. So what I need to know now, what is going
Zero
to
to
be
zero
the
po
range?
would it be 0 to 0.6?
Okay, did you say 0
To
to
0.6?
0.6?
Yeah.
Okay, now let me say the range of the exponential is s greater than 0. Okay, do you see that? I'm giving you more clue. You try. You have my
Oh,
you have my 1 point of extra credit now. Can
would
you
it be
try more?
yeah, 0.6 to 1, sorry.
Okay, you said 0.6 to 1. This is s greater than 0. S greater than 0. That means 0 to infinity, right? For the exponential, right?
Uh,
So which is going to be 0.6 to
Infinity.
exactly.
Okay.
Now 0.6 to infinity. Now, when H naught is true means plug in theta equal to 1 into the given expression into this guy here. So which means this is the one you want to find. Does that make sense? So I think you all understand that now, right? That is the way that guy is actually going to be. Don't forget, if you want to find the probability, okay, of type 1 error, rejecting H naught, when H naught is true, and don't forget, you have to use the suggested critical region. The suggested rejection region is S greater than 0.6, as you can see. That is where then you're going to start from that 0.6 and end in the upper bound of the given distribution. Right now, because exponential has an upper bound of infinity. Maybe in the day of your exam, it may not be infinity. It could be a number. You understand what I mean? Pay attention. So I'm just going to figure out the probability of that. That's going to be my the probability of type 2 error, of type 1 error. Now, how am I going to get, let's say I now ask you to obtain the probability of type 2 error. Okay. Now it's going to be reject HO, okay, when H1 is true. Oh, sorry. That is not correct. Let's start with power. There are two ways to get the probability of type 2 error. Power of a test and probability of type 2 error are related. If you want to get probability of type 2 error, you can first get the power of a test. Then you subtract the probability of power of a test from 1. Okay, so which means this is 1 minus beta, why the probability of type 2 error is beta. Now, if I want to find the probability of type 2 error here now, Okay, if I want to, if I want to get the power of a test, the power of a test ability to take correct decision, which is going to be reject HO when the alternative is true. That's the power of a test, right? That's a good decision, right? So if I want to do that now, so based on what we are actually doing, okay, if I want to get my power of a test, so my power now, okay, don't forget my power is 1 minus beta, which is equal, and don't forget the beta is the probability of type 2 error. Now you're actually going to go from, the other time, okay, so it's still going to be the same range to infinity, but what you're going to use will be different. You are going to use this guy, okay, you're going to use the theta under the alternative. Okay, is there any question? So right now it's going to be 1 over 1.5 exponential raised to power this 1.5 ds. That is what you're going to use get uh to get that. But and the moment you get this, you can get your beta. But if you want to get your beta directly, there's a way you can get your beta directly. The only way is just you're going to change. You're going to take the inverse of the greater than. Okay, if you want to get beta directly, you're going to use a less than, which is going to be 0 to 0.6. Okay, that is going to be. But what I'm trying to say, you can get power first using the same rejection region, the same rejection region that you use. In order not to cause any confusion, if I were you, okay, if a question asks you the probability of type 1 error, you're going to use the same rejection region, okay, except that the values of your theta will be the one in the non-hypothesis, okay, and the state space is going to be, now it's going to be 0.6 because it's greater than, going to be 0.6 to the upper bound of the distribution. But so then get your power. If you want to get your power, it's still going to be the same state space. But in the distribution, the theta you're going to specify will be different. It's going to be the theta value in the alternative. And the moment you get your power, you can get the probability of type 2 error by saying power, 1 minus power that you got is going to be probability of type 2 error. Okay, so I quickly want to move. Okay, we're going to ask you both power and the probability of type 2 error. Now I want to get to question 4. Question 4, we give you a distribution and ask you to show an expression for the best critical region. You're also going to do NEMA, NEMA. Okay, but this time around, they are not going to base it on one observation. It's going to be on, they're going to say sample size, which means, your X now is not just going to be X, is going to be sum of X. Okay, so you're going to use the ratio of the likelihood by NEMA, NEMA. Okay, and we want to show, we've already given you what you're going to show. We've given you the last expression, but we just wanted to show that, work your way, okay, up to that very expression, okay? So they're going to ask you to, whether they say the most powerful critical region, the most powerful critical region is the same thing as the most powerful test. It's the same thing as the best test. You're still going to use the idea of NEMA NEMA theorem. And that's going to be problem 4, part 1. Now in problem 4, part 2, that will test your knowledge of sufficiency. They're going to give you a distribution, and we're going to ask you to use the knowledge, to use official NEMA factorization, where you need to get the likelihood function of the distribution. Then you factorize that into 2 functions in such a way one has a parameter in it, the other one does not have a parameter in it, and the one that has a parameter in it is the one that contains the sufficient statistic. Okay, problem 5. Problem 5. Oh my God. Problem 5. We're going to test your knowledge of non-linear model. Non-linear module. They're going to give you a specification. If you follow what we did in class, they're going to give you a specification they're going to give you a non-linear specification where you're going to be the one that we introduce log to both sides. When you introduce log to both sides, then you're actually going to use the idea of linear technique. Okay. And we're going to give you data. Okay. You follow. I need you to revisit. I remember when I was walking you through a data set on crocodile in center Florida. So excuse me. So I needed to revisit that example in class. Very, very crucial. Okay. Now they're going to ask you the question they're going to say linearize the model. Okay. And estimate the parameters in the model. Since it's a multiplicative model, since it's a nonlinear model, you need to first introduce logarithm to both sides. And after introducing logarithm to both sides, then you're actually going to compare that to simple linear regression and follow the way like that. Okay. And after that, they're going to ask you to construct a confidence interval for a particular parameter. Okay. So what I need you to do is to actually revisit your lecture notes. Okay. And that's all about the problem in the final. You're actually going to have 5 problems in the final that I've already disclosed the area right now, and all what you need is just to revisit them. Is there any question at this time?
Can you repeat what part B was of that?
Okay, you mean the part B, you said should I repeat what part B of problem 5
Yes,
was,
please.
right?
Yes, please.
Okay, thank you for asking that question. The part B is going to be obtain the confidence interval of the parameter. You
Oh,
remember
okay, okay.
in
I
the
thought you said
linear.
that was C.
Oh, okay. So in the B, that's going to be obtain the confidence interval of the parameter, but in A is going to tell you linearize the model. And after linearizing the model, they use the data to estimate the parameters.
Okay,
Okay, does that make sense now, right?
yeah, that does.
Okay, that is going to be a problem. Oh my God, I'm actually going to be the greatest professor in the world if the least in this exam is 99% score, which is possible. Let us make it happen. You already know the areas where the exam is going to come from. Let's make it happen that for the first time in the history of the world, we want the minimum score of the student to be 99. That is achievable. Now you know the areas. Okay, is there any other question? Okay, in the absence of question before,
Actually,
oh, okay,
I
go ahead.
kind of have like a request. So for the fifth problem, could you make it like a decently smaller data set just because it takes a
Exactly,
while to calculate SXX and SX?
exactly. Yeah, it's going to be a smaller data,
Okay, thank you.
just like the way you requested. Yeah,
Thank you.
yeah, I'll do that. Okay, any other question? Okay, so I got quick announcement to make before I go. You know, at the end of the semester, they expect students to actually rate the quality of teaching they got. And of course, I will need you to go to the canvas. There is student, they call it SRT, which is student written of teaching. The university want to hear from you, about how I handle this class, and of course, how, what are the room for improvements? Okay, so they need you to actually answer some questions. Of course, I'm also going to send information about that, but that is part of your responsibility. At this junction, I want to appreciate every one of you, for I'm going to say it's a privilege to be a professor or instructor this semester. You guys have been great student. You listen, you ask questions, you make my work, so enjoyable because you know why the greatest professor in the world, that very greatest will not reflect if the students refuse to cooperate with instructor. But I'm going to say your own is different. You actually, from the one, you cooperated with me, and, what I'm going to say is this, this exam, it doesn't matter whether you have not scored it before. But this exam, if you actually review what I've asked you to review right now, this is being recorded. I'm actually going to publish this. Just make sure before the exam you listen to the information again and you review your lecture material. Oh my God, you're actually going to be fine. And of course, the probability of getting A in this course is going to be so high. Just like what I used to say, you know, success in life. Getting success is a very difficult and highly complicated task. Anywhere you find yourself in the world to, getting success is not easy at all. There's always going to be a barrier. Don't forget, we live in a stochastic environment. We live in a probabilistic space. And of course, and that is the reason why we actually need to have what I call a strong determination, to be able to accomplish whatever we've set aside to accomplish. But what I'm going to tell you, whatever situation you face, do do not give up. Okay, all what you just need to do is, take your time. Take your time, okay, review what you're supposed to review, and I'm going to tell you, you actually are going to undo and simplify complicated situation. Just like what I used to tell students, everyone around me, we are on the race, we are on the road to success, and the road is very narrow because there's a lot of people in this world, that are acquiring success. But let me tell you this, it is not all of them that is determined. I'm going to say that again. It is not everyone in the world that is, looking for success, that is determined. And that is the reason why some people, they're going to wait. Why some will go? Who are those that will go? Who are those that will wait? That very question is left to every individual to answer. But let me tell you this, when you have the spirit of perseverance, when you have the spirit of endurance, I'm actually going to tell you, and you have a very strong determination, they're going to wait for you. They're going to say, okay, you can go. Always tell yourself, I will be the greatest. I will be among the greatest scientists or greatest person in the world. That is actually achievable. That depends on how you display some spirit of endurance, some spirit of perseverance, because on the road to success is not easy. There's going to be a lot of barrier. And that's why I used to tell people around me, you just don't rule out yourself in anything. Don't give up because, there's possibility we could fall, within the sarcastic world. When you fall, pick yourself up. It doesn't matter the numbers of times I fall, but I am seeing success as the ability to rise and rise after many falls. It doesn't matter whether I'm going to fall, but provided I can pick myself up, I'm successful. Failure in life to me is not falling down, but staying down. That is the failure. Why I'm actually seeing success as ability to rise and rise after many falls. Let me tell you, I've fallen before. I pick myself up, and there is a tendency to fall again. But if I still have that ability to pick myself, even though I don't pray to fall, but don't forget, we live in a world where, due to an accidental, the charge of nature, at times we could fall. But when we fall, okay, let us pick ourselves up. Okay, like I said, once again, believe in yourself. Don't give up. Whatever you believe, whatever might conceive, it can happen. Make it happen. And I wish you the best in your career. So I'm going to see you again in person or during the day of exam. Okay. You don't need any statistical table at all for this exam. You don't need any statistical table at all. Somebody is going to say, what about for confidence interval? Because I mentioned in problem 5, it's going to be confidence interval. Okay. In class, there could be some suggestion about that. It's going to be, let me tell you this. If there's going to be confidence interval at all, okay, it's just going to be for 90% or 95% or 99%, or to be at the safer side, I can say, okay, maybe you're going to need a T table, but whatever table you need, I will bring that to the exam. Okay, is there anyone want to ask question before I close the session for the day? Is there anyone who need clarification or want to say something else? Okay, in the absence of that, make sure you all stay safe and have a lovely day. See you on Monday. Bye for now, everyone. Thank you too. Thank you, everyone. Thank you. Yeah. Thank you too. Yeah.